Hello, students. So, in the video you just watched, we explored details about the graph of sine and the graph of cosine in that order. Now, if we know what the graph of sine looks like and the graph of cosine, well, then surely we can figure out all the other trig functions because they're just built out of sines and cosines. Let's start with tangent. So let's try to plot tangent of x, which is sine of x over cosine of x. Now, one thing we could do is we could do exactly the same as we did when we graphed sine, like plot some actual points, connect them with little curves, and see what the graph looks like. We could, but I won't. Instead, I'll do this. So, well, just like sine, I will do something that I did just as I did with sine. We only need to graph it over a single period. And let's just remember what the period is by computing the tangent of x plus pi. And you know what I'm about to write, right? What is tangent? That's the same as the sine of x plus pi over the cosine of x plus pi. So adding pi to an angle, that corresponds to a reflection over the origin. So that means the sine of x plus pi is the same thing as negative the sine of x. Cosine of x plus pi is negative the cosine of x. These negatives will cancel, right? Negative divided by a negative becomes positive. And so you end up with just tangent of x. So what we see here is tangent of x plus pi is the same thing as the tangent of x. So this means, in fact, I think this one will be green. What this says about graphs is the graph of that function will be the same thing as the graph, will be the same thing as the graph of tangent x shifted left by pi. So the graph of tangent of x shifted left by pi is apparently the exact same as, coming from this piece, the graph of tangent of x. So the function repeats every interval of length pi. So this function has period. The period of tangent x is pi. That's an important fact to remember. And just for the sake of comparison, let's remember. So if you want the period of cosine, it's 2 pi. Of sine is 2 pi. Of tangent, apparently, is pi. Nice. So what does that mean? That means that if I can figure out what the graph of tangent looks like from 0 to pi, then I'll know what the graph of tangent looks like everywhere. Because what will I do? I'll take whatever I wind up with from 0 to pi, and I'll repeat it from pi to 2 pi, and I'll repeat it from 2 pi to 3 pi, and I'll repeat it from 3 pi to 4 pi. I'll repeat it from 0 to negative pi. I'll repeat it from negative pi to negative 2 pi. So I'll be able to completely understand the graph of the function by doing that. So I still have to understand it between 0 and pi. So tangent is built out of sine and cosine. So let's remember what sine and cosine look like. Well, between 0 and pi, well, I'll graph them both. Well, okay, now we'll just do them one at a time. So sine of 0 is 0. Let's see, draw the unit circle. Sine of 0 is 0 because that y-coordinate is 0. And then I'll start rotating up. So sine will become positive. It maxes out at a right angle. So at pi over 2, it maxes out to a value of 1. So sine climbs. It maxes out at pi over 2, 1. And then the y value of the graph goes back down. So sine goes back down until it gets down to 0 at pi. So this blue one is the graph of sine of x. If you want cosine of x, well, cosine of x starts at 0, 1. as the angle increases, the x value is getting smaller. So cosine gets smaller until it is 0 when the angle is pi over 2. It becomes negative until it gets to a negative 1 at pi. So, by reading these off, we can see lots of things, but we can see where these things are positive or negative. Cosine is positive from 0 to pi over 2, negative from 0 to pi. Sine is positive from 0 to pi over 2, and positive from pi over 2 to pi. So tangent is sine over cosine. So that tells me everything. So between 0 and pi, tangent will be positive divided by positive is positive. Between pi over 2 and pi, tangent is positive over negative is negative. Nice. So let's encode that in this graph. So tangent will be positive here and negative here. So the next thing that I think I want to keep track of is where are the vertical asymptotes and where are the x-intercepts. So x-intercepts are where the thing is 0. So tangent of x is 0 whenever sine of x over cosine of x is 0. But the only way that a fraction can be 0 is if the numerator is 0. When does that happen? Well, that happens when sine of x equals 0. And maybe you could do that by just trying to remember, but we have the graph of sine of x. Looks like it's 0 at pi. It's 0 at 0. Well, right now I only care about the interval from 0 to pi. That's why I didn't list negative pi or 2 pi or anything more extreme than that. So let's indicate that. So tangent of x is 0 when x is equal to 0 and is 0 when x is equal to pi. Tangent has a vertical asymptote whenever the denominator of this fraction is 0. When is the denominator equal to 0? Well, that asks when is cosine of x equal to 0? Well, cosine is the red curve at pi over 2. So there will be a vertical asymptote at x equal to pi over 2. Cool. That is a perfectly straight vertical line. So let's just use those for x to figure out what the graph should look like. So it has this x-intercept, and then it becomes positive immediately. And it needs to make it to this vertical asymptote. It can't go to negative infinity, so it looks like it'll have to go up to positive infinity. From this x-intercept, if I go left a little bit, it becomes negative. Then I need to get to that vertical asymptote. I can't go to plus infinity, so I have to go to minus infinity. So there's the graph of tangent between 0 and pi. Oh, nice. So if I know the graph of tangent from 0 to pi, I should be able to use periodicity to fill in the rest of it. So I know there's an intercept at 0, an intercept at pi, a vertical asymptote goes up like this. Now, if we want to graph tangent over the rest of the real line, I'll just take that pattern and repeat it. And if I were cleverer, since this is a computer, I would figure out how to just do a copy-paste type thing, but I'm not clever enough. So I know that this pattern from 0 to pi will be exactly the same pattern as I see from pi to 2 pi. So there will be a switch colors. Vertical asymptote at 3 pi over 2. the thing will increase to get to that vertical asymptote. Then it'll jump to minus infinity and get back to 2 pi. So I've drawn the exact same picture again. Then it will repeat again from 2 pi to 3 pi. It will repeat again from 3 pi to 4 pi. It will repeat between negative pi and 0. Nice. So now that we've got this hand-drawn graph, let's see how well we did at reproducing how the graph actually looks. All right, and there it is. There's the graph of tangent of x from negative 2 pi to 4 pi, a computer-generated graph, so this evaluated a bunch of inputs, and those are the outputs it produced. I think we did a pretty good job capturing the same idea. Groovy. So, let's make some observations about this. This function, it appears as though, and I still don't know how to do a correct reflection, so I won't try. If you were to take this and reflect it over the origin, or rotate it 180 degrees about the origin, you'd get the exact same graph back. So it sure looks like tangent of x is odd, but in fact that's something that you should already know. To check for oddness, you evaluate tangent of negative x. To evaluate tangent of negative x, that's the same thing as the sine of negative x divided by cosine of negative x. Sine of negative x is negative the sine of x. Cosine of negative x is cosine of x. Yeah, that gives me negative tangent of x. So that checks out. Where does this function appear to be increasing? Well, at 0, it looks like it increases really, really, really fast. At pi over 2, something really weird happens. It jumps down from plus infinity to minus infinity. So there's this jump of infinite length at a point that's not in the domain, and then it starts increasing again. So I would say this function is increasing on its whole domain. The slope is always positive. That doesn't say it's always increasing, just on its domain. What other observations do we see? It looks like it has an x-intercept at 0, pi, 2 pi, 3 pi, and so on. So it looks like every multiple of pi. It's got a vertical asymptote, it looks like, at pi over 2, at 3 pi over 2, at 5 pi over 2. In fact, one way of describing these is, well, all of these vertical asymptotes are somehow the same vertical asymptote. They're just this vertical asymptote, but shifted by some pi's. There's this vertical asymptote, shifted left, shifted right by pi, shifted right by 2 pi, shifted right by 3 pi. So in general, there's a vertical asymptote at pi over 2 plus any multiple of pi. Cool. So if we can do all that for tangent, surely we can do it for cotangent too. Maybe I'll stop and upload this video, and then we'll talk about cotangent in a moment.